Hello, good morning. Welcome to the series of videos on digital signal processing. We first start with DFT, Discrete Fourier Transform. Myself, Dr. Shaila Dinkar Apte. Let us first see what is DTFT and what is DFT. So, we have something, let us consider some signal xn, which is a band limited signal. This is a band limited time domain signal x of t. It is band limited with some bandwidth equal to W. If the bandwidth is W, we can easily sample it using sampling frequency which is greater than or equal to 2W. So we are considering the multiplication of this signal with a train of impulse so that we can sample it. And how this train of impulse should be, it should have a frequency which is greater than or equal to twice W. And then after we multiply the signal xt with the train of impulse, we get this sampled signal. This is called as discrete time signal and we denote it by x of n. Now, when we do the process of sampling, what we are doing actually is signal in time domain is multiplied by the train of impulse. Now, what will happen in the Fourier domain? In the Fourier domain, there will be convolution. So, time domain multiplication results in the convolution in the spectrum domain. So, we will have a convolution of spectrum of the signal xt with the spectrum of the train of impulse. So, let us see how the spectrum of x of t will be represented. Customarily, we represent the spectrum of xt as a triangular spectrum which is shown with a triangular shape with a bandwidth of W. It does not necessarily mean that it will have a triangular shape, but we represent it with a triangle, saying that it will have the bandwidth between 0 to, it will have frequencies between 0 to W and it will have a bandwidth equal to W. Now the train of impulse in time domain will result in a train of impulse in the frequency domain with the separation of fs, where fs is a sampling frequency. This sampling frequency will have to be proper in the sense it should be greater than or equal to 2W so that there is no aliasing occurring in the time domain. So this is the representation of the spectrum of the signal. As I said, it is represented by a triangular shape and the maximum value is a W. So W is the bandwidth of the signal. This is the representation for the spectrum of the signal. Now the spectrum of the train of impulse will again be a train of impulse, but it will have a separation of Fs, where Fs is the sampling frequency. And when we convolve these two, convolve the spectrum of the signal with the spectrum of the train of impulse, it will result in a replicated spectrum. So there will be a triangular spectrum appearing at 0, then at Fs, minus Fs, and so on. It should appear at 2 Fs, 3 Fs. It should also appear at minus twice Fs, minus 3 Fs, and so on, up to infinity. But you will find that it is periodic with a period of Fs. In terms of angular frequency, if we want to represent, it will have a period of 2 pi. So the spectrum that exists is a continuous spectrum and it will have the periodicity of 2 pi. Now, if it is a continuous spectrum, how can we process it with our digital computer? It is not possible. So what will have to be done is you will have to sample it properly in this frequency domain. So what are the conclusions from the frequency domain picture that we have seen? The convolution of the spectrum of the signal and the spectrum of train of impulse generates a replicated spectrum on either side with a gap of Fs, where Fs is a sampling frequency. And in terms of angular frequency, we can say the gap will be 2 pi. So it will be replicated spectrum after every 2 pi. As the spectrum is periodic and repetitive, we need not concentrate on the entire spectrum. We can concentrate only on one period of the spectrum, that is between 0 to 2 pi. So it is a continuous spectrum that is called as DTFT, discrete time Fourier transform of discrete time signal. But because it is a continuous spectrum, it cannot be processed using our digital computer. So we need to sample it with proper sampling frequency in the frequency domain. So after we sample this particular periodic spectrum between 0 to 2 pi, we get the sampled version of DTFT, and it is what we call it as a discrete Fourier transform. So sampling in frequency domain. So we'll have to take one period of the spectrum, that is between 0 to 2 pi, and we'll have to sample it properly in frequency domain. If we sample it with equidistant n samples, we get capital N number of discrete Fourier transform coefficients. So discrete Fourier transform is nothing but a sampled version of DTFT. Now again, similar to when we sample in time domain, we see that the sampling frequency should be greater than or equal to twice it should be greater than or equal to twice W, where W is the bandwidth of the signal, so that there is no aliasing in the time domain. Similarly, if we sample the frequency domain signal properly, we'll have to sample it so that when we recover the time domain signal, there is no aliasing in the time domain signal, right? So how many samples you should take in the DFT? So when we sample it, we are getting the sampled version. How many samples we should consider? We should consider capital N number of samples. How these capital N number of samples should be? Capital N should be greater than or equal to L. It should be ideally greater than L, where what is capital L? Capital L is the actual number of samples in the original time domain signal. So the original time domain signal, which is aperiodic and with band limitation of W, suppose it has, if we have sampled it with proper sampling frequency, and if we are getting capital L number of samples in it, then when we sample the frequency domain picture, we'll have to consider the number of equally spaced points in the frequency domain equal to capital N, where capital N will have to be greater than the actual number of samples in the time domain. If this is so, then we can write x omega. This is the formula for your DTFT. Xn, this is the discrete time signal, e raised to j omega n. Now the j omega n, we are supposed to, this omega axis, which is between 0 to 2 pi, which is periodic, we are supposed to sample it. So wk is representing the kth sample, which is equal to 2 pi k upon n, because 2 pi we are dividing it into capital N number of samples. So how we can write xk, that is the DFT coefficient? It is n varying from 0 to n minus 1 xn e raised to minus j 2 pi k n divided by capital N. This becomes the formula for DFT coefficients. Now we'll have to always see that capital N will have to be greater than or equal to capital L, where capital L is the total number of samples in the original time domain signal. So whether we write it as 0 to n varying from 0 to n minus 1, or whether we represent it as n is equal to 0 to n minus 1, it is same thing, because after L the samples will be 0. If L greater than L, no aliasing will occur in the time domain when we recover the time domain signal. So Xn can be recovered from the DFT coefficients. So this is the corresponding frequency domain signal, which is periodic between 0 to 2 pi. What I am doing is, between this period of 0 to 2 pi, I am taking capital N number of samples, where how capital N is, this capital N will have to be greater than capital L, because the signal contains only L number of samples. Further samples are not there, and I am considering capital N as the number of samples for sampling in the frequency domain. Then what will happen when I recover the signal? I will get all these first L samples, and after that I will get further zeros. So clear separation will be there, and I will get the signal properly recovered in time domain. Now what will happen if n is less than n? That is, I am considering the number of samples for sampling in frequency domain, which is less than the actual number of samples in the time domain. In this case, what will happen is, The second uh, replication of the spectrum will start from capital N. This capital N is now less than capital L. So in this case, what will happen? The capital L number of samples will exceed and they will encroach the area in the second period. And what will happen? They will overlap with these further samples. They will also overlap in the next further period. They will also overlap with the next further period samples. So see what will happen here. So suppose I am taking the signal xn is equal to a raised to n un. Suppose let us say a is equal to 0.8 and I am considering capital N is equal to 15. Now in this case, how many samples are there? It is appended by un. That means there will be infinite number of samples. So actually the sampling is not possible because the bandwidth is infinite. But let us say that we sample it and we take the sampling frequency so that we are getting only we are using capital N, that is the periodicity in the frequency domain. Sampling, we are considering it as 15. 15 is much less than infinity. So what will happen when I recover the samples in the time domain? I will have the signal at sample number 1. It will also be say it will also replicate, sorry, it will also, you can say, overlap with the sample at sample number 16, sample number 32, sample number 64, and so on. And the addition of all these samples will appear as the recovered sample. So what is the actual sample? Actual sample is 0.8 at n is equal to 1. But what will happen to the recovered signal? Recovered signal sample will be 0.8292. So there is a difference of 0.0292. How you attribute this? You attribute this to the overlapping samples x of the sample appearing at 16th, 32, 64th, then 128, 256, and so on samples. So all these samples will overlap and you will get the summation, which is resultant that I have put it here, which is approximately 8292. There can be further resolution also. I have just represented it in resolution with 4 digits. So it is 0.8292. The second sample will also be overlapping with the 17th sample, then 33rd sample, 65th sample, and so on. So it will also have the difference with respect to the actual signal sample. That means we see that the signal samples get aliased, and because of the aliasing there will be, and aliasing will cause the overlapping and there will be difference in the actual sample that will be recovered. So faithful reproduction is not possible. This is why this is happening, because the actual signal is having infinite samples and we are using the sampling frequency which is less than the actual bandwidth. That means the signal that is sampled, the signal actually it cannot be sampled, you can say. And in that case, when you sample the DTFT, you are not using sufficient number of samples. Actually capital N should be how much? Capital N should be infinity, but we are using only capital N is equal to 15. Instead of 15, if I use 150, still I will have the first sample, then I will have how much it will be? 150 plus 1, it will be 151 sample, then 301 sample, and so on. So the corresponding samples will overlap. So still there will be overlap and there will be aliasing, but the amount of aliasing may be less if I am using no number of samples in capital N. So do you understand what is aliasing here? In when you not sample, do not sample properly in frequency domain, you get the aliasing in time domain. When you do not sample properly in time domain, you get the aliasing in the frequency domain. What is aliasing in the frequency domain? We get the corresponding spectra overlap. Now, the second question is, now can we recover DTFT from DFT? We have sampled the discrete time Fourier transform and we are getting discrete n number of samples. Now, from these n number of samples, can I get the continuous spectrum? The result is yes, you can get it. This is the corresponding formula for x of k. And what I should do, I should take the summation from n equal to 0 to n minus 1, and this is e raised to minus j omega n. So if you just simplify, you will get this sine omega n by 2 divided by n sine omega by 2. You can recognize this as a sinc function, but this sinc function is a periodic one, so it is not same as your sinc function, which is varying from minus infinity to infinity. For the interpolation that we used in the frequency domain, but in this case, this particular frequency domain sinc function, interpolation function, is also called as Lagrange interpolation, and it is periodic. And because it is periodic, how it would look like? It would look like this. It is between existing between minus pi to plus pi, because this is periodic with a period of 2 pi. So that is why the interpolation function will also be periodic between minus pi to plus pi. But of course, it will have the resemblance to the shape of your sinc function that we already know. Now, in the next episode, we'll consider the properties of DFT. Thank you. Let us consider the relation between DFT and the Z transform also. Consider the ROC that includes the unit circle. So we have the DFT formula. We also have the Z transform formula. This is the Z transform formula. X and Z raised to minus n. And if we sample this zk, if we write it as e raised to minus j 2 pi k by n, and if I write sample, if I take xk as xz, which is obtained at zk equal to e raised to j 2 pi k by n, I get this formula, which is the formula for DFT. So what is the meaning? If we sample xz at n equally spaced points on the unit circle, you will get the DFT coefficient. So there is a relation between the DFT coefficients and the Z transform, provided the Z transform includes the unit circle, and on this unit circle you consider n equally spaced points, then you will get the DFT coefficients.